Good afternoon, or welcome to the lecture of major and integration. Okay, so today we will see what is an Radon Nikodym theorem. First, we will see one note. I think this note will be a converse part of Radon Nikodym theorem. Okay, so see the note. Let mu be a measure on capital X comma curly b. That is a measurable space capital X comma curly b, and let f be a non-negative measurable function, negative measurable function defined on capital X. Define one major gamma, define major gamma from curly b to the 0 infinity union infinity by gamma of e is nothing but integration over a set e f of d. Okay, so this will be our measure given things. Mu be a measure on measurable space xb, f be a non-negative measurable which is defined on the universal set ex, and gamma is a measure which is defined from curly b to r plus union infinity or close to 0 to infinity union infinity by gamma of equal to integration over set e of f d mu. Okay, now as f is a non-negative measurable function, non-negative means f is greater or equal by 0. As f is greater or equal by 0, then there is one property integration over set e of f is d mu is must be greater or equal by 0. Since as f is non-negative, then its integration must be non-negative only. But integration over set e of f d mu is nothing but gamma of e. Therefore, gamma of e is greater or equal by 0. As gamma is a measure, then it must be first here we have to check first whether gamma is a measure. It is just a function now here. Gamma which is defined from curly b to close the 0 infinity union infinity, and which is defined by gamma of equal to integration over set e of f d mu. But as each f is non-negative measurable function, therefore integration must be greater or equal by 0. As integration is greater or equal by 0, then which is nothing but the gamma of e, and gamma of e is non-negative here we get. Now, as already we have given that domain of this gamma will be a sigma algebra, then there is no need to prove again. It will be a defined on sigma algebra. Now it remains to check the two properties, that is gamma of phi will be equal to 0 and gamma is closer than the countable additive. Let us first consider gamma of phi. Gamma of phi by definition it is nothing but integration over set phi of f d mu. But we know that the integration over a set of measure 0 is always 0, as here phi is a set where integration is defined on the set phi, and measure of phi will be equal to 0. Therefore, as integration over a set, integration over a set of measure 0, measure 0 is always 0, is 0. Okay, so which implies gamma of phi must be equal to 0. So first property will be 2. Okay, now second one, let ei be a sequence of disjoint measurable sets. Disjoint measurable sets. So consider gamma of union over I running from 1 to infinity ei, and which is nothing but by definition integration over set union over I running from 1 to infinity ei is nothing but integration over set f of integration of function f of d mu. But we know that integration over union over I running from 1 to infinity ei, if each ei is a sequence of disjoint measurable set, then integration over union is nothing but the summation of integration. Therefore, it is nothing but summation I running from 1 to infinity integration over set ei of f d mu. But summation I running from 1 to infinity as it is, integration over set ei of f d mu by the given definition of gamma of e. Gamma of e is nothing but integration over set e of f d mu. Then this part. Integration over set ei of f d mu. By definition, it is nothing but gamma of ei. So which is equal to summation I running from 1 to infinity gamma of ei. So here actually we have proved gamma of union over I running from 1 to infinity ei is nothing but summation I running from 1 to infinity gamma of ei, and which is the property of countably additive, which implies gamma is countably additive. As gamma of phi will be equal to 0 and the gamma is countably additive, which by the definition of major, which implies gamma is a measure on curly b or measurable space x comma curly b. Okay, so here we get gamma is a measure on x comma curly b. Now let e belongs to curly b any arbitrary set. Let e belonging to curly b be any arbitrary set. It means it is a measurable set. And if we consider, we take measure of e will be equal to 0, then by the definition gamma of e equal to integration over set e of f d mu. Here the integration over the set mu and measure of e will be equal to 0. Again here we get the integration over a set of measure 0 is 0. We know, and here measure of e will be equal to 0. Then by this property, that is integration over a set of measure 0 will be equal to 0. Then gamma of e must be equal to 0, which implies gamma e is equal to 0. So if we take e belonging to curly b be any arbitrary set and measure of that e will be equal to 0, then gamma of e must be equal to 0. Then by the definition of absolutely continuous measure, if mu and gamma are two measures, then the measure gamma is said to be absolutely continuous with respect to mu. Whenever measure of e will be equal to 0 for any e belonging to curly b, then gamma of e is also equal to 0. So here we have taken one arbitrary e and considered measure of equal to 0, then gamma of e is also 0. Then by the definition of absolutely continuous measure, which implies gamma is absolutely continuous with respect to mu. Okay, so from this we conclude that, so if f is a non-negative measurable function, negative measurable function, then then there exists a measure gamma which is absolutely continuous with respect to me, which is absolutely continuous with respect to me. Okay, so here we get f is a non-negative measurable function, then there exists a measure gamma which is absolutely continuous with respect to mu. Now its converse part is also true. If there is a measure mu and gamma in which gamma is absolutely continuous with respect to mu, then there exists one non-negative measurable function such that gamma of equal to integration over set e of f d mu. Its converse part is also true, and that part is called as a Radon-Nikodym theorem, and that we will see in today's lecture. Okay. Now let us see what is a Radon-Nikodym theorem. See its statement. Let capital X curly b mu be a sigma finite measure space, a sigma finite measure space, and let gamma be a measure defined on curly b, okay, which is absolutely continuous with respect to mu, which is absolutely continuous with respect to mu. Then there is a non-negative measurable function measurable function f such that for each set each set E belonging to curly B, we have gamma of E is nothing but integration over set E of D mu. Further, if G is any other measurable function, other measurable function with this property, then G is nothing but F almost everywhere with respect to the measure. Okay. So here it's cannot what we have already proved, that is if F is a non-negative measurable depend on a measurable depend on capital X. Then there exists one measure gamma which is absolutely continuous with respect to mu. But here Radon Nikodym theorem we have given two measures gamma and mu, in which gamma is absolutely continuous with respect to mu, and from that we have to prove that there exists one non-negative measurable function f such that gamma of E is nothing but integration over set E of f d mu. And after that we have to prove the uniqueness of such a function, and if possible there exists one some G function with these same properties, then G and f are same with respect to the measure mu. Okay, first we will prove this theorem for a finite measure space, and after that we will extend it to a sigma finite measure space. So see it's prove. Proof. First we will prove first we will prove the theorem for finite measure space. Measure space, and then we will extend it to sigma finite measure space. Sigma finite measure space. Okay. So now let alpha be any rational number. Any rational number. As alpha is any rational number, then for each alpha, for each alpha, gamma minus alpha into mu is a signed measure. Signed measure. Since here we don't know which measure will have a larger value. Both gamma and mu are measures, and we know that the linear combination of measure is always not a measure. It may be a signed measure. Since it is always it is not necessary that always it will be a non-negative. So here as alpha and gamma are measures, but gamma minus alpha into mu will be a signed measure. Okay. Let A alpha B alpha be the Hahn decomposition of X. Hahn decomposition position of X corresponding to a signed measure gamma minus alpha of u, alpha of mu. Now, as here we have taken alpha be any arbitrary rational number, as 0 is also a rational number, then put alpha equal to 0. Let alpha is equal to 0. Then alpha equal to 0, then the signed measure gamma minus alpha mu becomes gamma minus alpha mu is nothing but gamma minus 0 into mu, and which is equal to gamma. And gamma is a measure. Now choose A naught is equal to x and b naught equal to phi. Okay, so here we have taken the hand decomposition. Hand decomposition means we have to get the intersection of x and b naught equal to phi. So as we have taken alpha equal to gamma equal to beta, then we have to get the intersection of b equal to x and b naught equal to phi. So as we have taken alpha equal to 0, take a naught equal to x and b naught equal to phi. But as gamma is a measure, then gamma of a naught equal to gamma of x is equal to gamma of x. As gamma is a measure, then it must be greater equal by 0, and a naught union b naught will be equal to x union phi, which is x, and b naught union beta will be equal to x union phi, which is beta. So and a naught again hand decomposition of x corresponding to a standard measure gamma or alpha will be equal to 0, then it is only the gamma. So here we get gamma of a naught equal to gamma of x will be greater equal by 0. Now let us consider b alpha minus b beta, standard measure gamma minus alpha mu, and b beta is respect to a standard measure gamma minus beta mu. Therefore it can be written as b alpha intersection b beta complement. Okay. Okay. So it is a negative set with respect to standard measure gamma minus of beta. So b beta is nothing but it is a complement of negative set. Therefore it is nothing but it's a positive set, which is b alpha intersection sum a beta. Okay, but a beta is a negative set with respect to standard measure gamma minus of beta mu. But a beta is a sign and b alpha is a negative set with respect to sign gamma minus of alpha mu, which implies b alpha minus of b beta is subset of b alpha, and b alpha minus b beta is also a subset of a beta. Okay, which implies signed measure of gamma minus alpha mu of b alpha minus b beta is less equal by 0, and gamma minus beta mu, since a beta is a positive set with respect to a standard measure gamma minus beta mu of b alpha minus b beta is greater equal by. Now after that, consider alpha and beta be any two real numbers or rational numbers. Alpha beta be any two rational numbers such that alpha is less than beta. As alpha is less than beta, then as measure mu is a measure, therefore it must be always non-negative. Then alpha into measure of b alpha minus of b beta, it must be less than beta into, okay, so equal by make this one. Now as if we take the minus sign on both sides, then the inequality reverses, which implies minus of alpha into measure of b alpha minus b beta is greater equal by minus of beta into mu of b alpha minus b beta. Okay, now as we have given that gamma is a major space which is absolutely continuous with respect to mu, and it is always a non-negative, it means we can add it on both sides, which implies gamma of b alpha minus of b beta alpha mu of b gamma of b alpha minus b beta minus of beta mu of b alpha minus b beta. But we know that gamma measures are always holds the linearity property. Therefore, it is nothing but gamma minus alpha mu of b alpha minus b beta, which is greater equal by gamma minus beta mu of b alpha minus of b beta. Okay, so here we get these measures now. But we have proved that gamma minus alpha mu of b alpha minus b beta is less equal by 0, and gamma minus beta mu of b alpha minus beta is greater equal by 0. So gamma minus alpha mu of b alpha minus b beta is less equal by 0. That is gamma minus alpha mu of b alpha minus b beta, and which is greater equal by gamma minus beta mu of b alpha. Prove this one, these steps. Okay, so as these measures are less equal by 0 and greater equal by 0, then both are same, which implies gamma minus alpha mu of b alpha minus b beta must be equal to gamma minus beta mu of b alpha minus b beta. Okay. Now, as we have added the terms gamma b alpha minus b beta and gamma b alpha minus b beta, then we get gamma b alpha minus b beta on both sides. Then we get minus of alpha mu of b alpha minus b beta is equal to minus of beta mu of b alpha minus b beta. Okay, so divide both sides by minus 1, then we get alpha of mu of b alpha minus of b beta, which is nothing but beta mu of b alpha minus b beta. Okay, now which is nothing but alpha minus beta of measure of b alpha minus b beta, and which is equal to 0. But we have taken alpha is strictly less than beta, that is the measure of b alpha minus b beta will be equal to 0. So it means alpha minus is measure of b alpha minus b equal to 0. Then only it is possible that measure of b alpha minus b beta into alpha minus beta will be equal to 0. But as alpha is less than beta, alpha minus beta is not equal to 0, then there is only one possibility, that is measure of b alpha minus b beta will be equal to 0. So here we get measure of b alpha minus b beta will be equal to 0. And in previous lecture we have proved one lemma, that is if capital X curly b will be a finite or sigma finite measure space, and for each and d be a dense set of real numbers, then for each set belonging to curly b, that is b alpha belonging to curly b, such that measure of b alpha minus b beta will be equal to 0 whenever alpha is less than beta, then there exists one unique non-negative, or there exists one extended real valued function f such that f is less equal by 0, or f is less equal by alpha on b alpha, and f is greater equal by alpha on b alpha complement, that is a alpha. Okay, so now by that lemma, so by previous lemma, this lemma, there exists a measurable negative measurable function f such that f is less equal by alpha on b alpha, and f is greater equal by alpha on b alpha complement, that is a alpha. Since b alpha and a alpha are the and decomposition of x with respect to sign the measure gamma minus alpha of mu. But here we have taken alpha is a rational number, therefore it is also true for alpha equal to 0. So take a naught is equal to x and b naught will be equal to 5, which implies there exists a measurable function f such that actually here that lemma we don't know the non-negativeness of the given existence of such function. It is just an extended real valued function. Okay, so there exists a measurable function f such that f is less equal by 0 on b naught, and f is greater equal by 0 on a naught, but a naught is x. Okay, so as f is greater equal by 0 on a naught, that is x, which implies f is a non-negative. Here we have proved f is a non-negative measurable function on x. Okay, so here we get one non-negative measurable function x. Now we have to prove that the gamma of e is nothing but integration over set e of f d mu, and after that we will prove its uniqueness. Here just we get a one non-negative measurable function which is defined on x. Okay, now let e belonging to curly b any arbitrary set, arbitrary set. arbitrary set. As we have given that major, mu is a sigma finite measure, as mu is a sigma finite measure, as it is sigma finite, then it must be finite. That is, measure of E is finite. Okay, so as measure of E is finite, then for epsilon greater than 0, we can choose a large n such that 1 upon n measure of E is less than epsilon. मेजर आहे म्यू मेजर आहे याचा अर्थ काहीतरी त्याची क्वालिटी पॉझिटिव्ह व्हॅल्यू असेल. पॉझिटिव्ह व्हॅल्यू आहे, फायनाईट मेजर असल्यामुळे फायनाईटी आहे, म्हणजे मी काहीतरी लार्ज एन चूज करू शकतो ज्यासाठी की फॉर गिवन एप्सिलॉन ग्रेटर दॅन 0 1 upon n measure of E is less than epsilon. For example, if suppose my measure of E will be equal to some 100, then we can take n as a 101, then 1 upon n measure of E must be less than epsilon. In this way, if whatever will be the value of mu of measure of E, we can choose one n such that 1 by n measure of E is less than epsilon. Now define the sets. Define the set EK as E intersection BK plus 1 by n minus of BK by n. Okay, and E infinity equal to E minus union over k running from 0 to infinity bkn. That is, we will define these two sets. Okay, now ek is nothing but A intersection bk plus 1 divided by n minus bkn, and E minus E infinity is nothing but E minus union over k running from 0 to infinity but E minus union by n are the negative set with respect to the standard measure gamma minus k by n, gamma minus k upon n by k upon n into mu, and gamma minus k plus 1 upon n into mu. Okay, so now where bk upon n is a negative set with respect to the signed measure gamma minus gamma minus k upon n into mu. Okay, similarly bk plus 1 by upon n is the negative set with respect to the signed measure gamma minus k plus 1 upon n into mu. Now, as E infinity equal to E minus union over k running from 0 to infinity bk by n, after solving this one, if we put the value of ek in this one, then we get the value of E as, or we can put the value of E in this first one, then we get capital E as E infinity union over k running from 0 to infinity bk, where each k is a disjoint measurable set. As each k is a disjoint measurable set, then gamma of E is equal to gamma of E infinity plus gamma of union over k running from 0 to infinity ek. But as gamma is a measure, then it is a goes under the countability property. Then it is nothing but gamma of E equal to gamma of E infinity plus summation k running from 0 to infinity gamma of ek. Take this one as some equation 1. Okay, now from given as defined sets ek is nothing but ek plus E intersection b k plus 1 divided by n minus of b k by n, which implies as ek is intersection of these two sets, then it must be a subset of both the sets, which implies ek is a subset of bk plus b k plus 1 divided by n minus of b k by n. But bk n by n is a negative set with respect to the signed measure gamma. Therefore, actually it is nothing but plus 1 divided by n intersection, k plus 1 divided by n intersection of bk n, bk upon n complement is nothing but ekn. Since bkn is a negative set with respect to the sign of major gamma, so ek is a subset of bk plus 1 upon n intersection a of k by n. Again we have to do one theorem. If mu is a major on capital X comma curly b and d will be instead of real numbers, then for each alpha there is a set b alpha belonging to curly b such that b alpha is a subset of b beta. For alpha less than beta, then there exists one extended real valued function f such that f is less equal by 0 on b alpha and f is greater equal by 0 on b alpha complement. That is, f is less equal by alpha on b alpha and it is greater equal by alpha on b its complement. Now here we get one subset ek, which is subset of bk plus 1 upon n and intersect, and also it is subset of ek by n, which implies ek is a subset of pk plus 1 divided by n, and then by that lemma we get f is less equal by k plus 1 divided by n on bk plus 1 divided by n, and f is greater equal by k by n on ek by n. Okay, and which is for the same set ek, that is here we are k by n, that is k by n is less equal by k plus 1 divided by n. Okay, and which is on ek. Now take the integration over ek over the set ek, which implies integration over set ek k by n of d mu less equal by integration over set ek of f d mu, which is less equal by k plus 1 upon n of, sorry, integration over set ek of d mu. But k plus 1 upon n and k upon n are the first, therefore they are nothing but k by n into integration over set ek of d mu. And by we know that if measure of e is finite and e belonging to curly b any set, then integration over set e of 1 d mu is nothing but measure of e. Therefore that one it is nothing but measure of ek, which is less equal by integration over set ek of f d mu, and which is less equal by k plus 1 divided by n of integration over set ek of, sorry, it is measure of ek. Again take this one as a sum equation to go. Okay, now as this one ek is a subset of bk plus 1 divided by n intersection ak by n, as ek is a subset of bk plus 1 divided by n intersection of ak by n. But we know that k plus 1 bk plus 1 divided by n is a negative set with respect to a sign measure gamma minus k plus 1 upon n into mu, and ak by n is a positive set with respect to a sign measure gamma minus k upon n into mu. Gamma minus k plus 1 divided by n into mu is less equal by 0 of ek is less equal by 0, and gamma minus k upon n of mu ek will be greater equal by 0. Okay, which is from the definition of positive and negative set. After solving this one, we get gamma of ek is less measure of ek, gamma of ek is greater equal by k by n measure of ek. So combining these two, we get k by n measure of ek is less equal by k plus 1 upon 1 measure of ek. So up to now, first we will consider this part. Okay, that is, this will be take equation 3. then this part. So as k by n, measure of ek is less equal by gamma of ek, which implies k by n, measure of ek plus 1 by n, measure of ek is less equal by gamma of ek plus 1 by n, measure of ek. This is from the second first part. But as again it is a linearity holds, then it is nothing but k plus 1 divided by n, measure of ek is less equal by gamma of ek plus 1 by n, measure of ek. Similarly, from the second part, take this one as equation 4. Now from this part, as gamma of ek is less equal by k plus 1 upon n, measure of ek, k plus 1 upon n, measure of ek. But this part can be written as k plus k divided by n, measure of ek plus 1 by n, measure of ek. So actually we get here gamma of ek is less equal by k by n, measure of ek plus 1 by n, measure of ek. Now just subtracting both sides by 1 minus 1 by n, measure of ek, then we get gamma of ek minus 1 by k by n, measure of ek. Take this one as equation 5. So equation 4 says that k plus 1 upon n, measure of ek is less equal by gamma of ek plus 1 upon n, measure of ek. And equation 5 says that gamma of ek minus 1 by n, measure of ek is less equal by k by n, measure of ek. Now if we put these values in this one, okay, k plus 1 upon n, measure of ek is less equal by gamma of ek plus 1 by n, measure of ek, and k by n, measure of ek is less equal by, sorry, gamma of ek minus 1 by n, measure of ek is less equal by k by n, measure of ek. So after putting these 4 and 5 in 2, we get 10. Equation 4 and 5 in 2, we get, okay, gamma of ek minus 1 by n, measure of ek is less equal by integration over set ek of and which is less equal by gamma of ek. So here we get this term. Take this one as equation number 6. So okay, finally we get gamma of ek minus 1 by n, measure of ek is less equal by integration over set ek of mu, and which is less equal by gamma of ek plus 1 by n, measure of ek. Okay, now adding all these inequality, as here k is running from 0 to k running from 0, 1, 2, 3 to so on. Since actually here alpha is any rational number and k by n we have taken, so k is running from 0, 1, 2, 3. After adding all these terms, we get, that is, first term would be nothing but gamma of e1 minus 1 by n, measure of ek, measure of e1 plus integration over set e1 of f denote, which is less equal by gamma of e1 plus 1 by n, measure of e1. Similarly for e0, e1, e2, e3. Then after adding all these, then we get summation k running from 0 to infinity, gamma of ek minus of 1 by n, summation k running from 0 to infinity, measure of ek, which is less equal by summation k running from 0 to infinity, integration over set ek of f d mu, and which is less equal by sum of ek plus 1 by n, summation k running from 0 to infinity, measure of ek, which is this will we get after adding all the terms, that is k running from 0, 1, 2, 3 and up to so. But we know that as gamma is the measure, then it is closer to contiguity. Therefore summation k running from 0 to infinity, gamma of ek is nothing but gamma of union k k running from 0 to infinity ek. So it can be written as gamma of union over k running from 0 to infinity ek minus of 1 by n measure of union k running from 0 to infinity ek, and which is less equal by, as here each k is a disjoint measurable set, hence summation of integration is nothing but integration over union, since ek's are disjoint measurable set. So it is nothing but integration over union over k running from 0 to infinity ek of f d mu, and which is less equal by again gamma of union over k running from gamma of union over k running from 0 to infinity ek minus of, sorry, plus of 1 by n measure of union k running from 0 to infinity ek. So this part will be get here. Okay, now take this part as a question number 7. Number 7. Now our infinity is nothing but our E infinity will be E minus union over k running from 0 to infinity bk by n. So actually it is nothing but E intersection union over k running from 0 to infinity b of k by n. Okay, so k by n complement. So therefore after solving this we get E intersection over k running from 0 to infinity bk by n complement, which is from the De Morgan's law. De Morgan's law. Okay, so which is nothing but E intersection over k running from 0 to infinity bk by n complement. But bkn is a negative set with respect to sign measure gamma minus k by n into mu. So therefore its complement will be positive set ak by n. So actually it is nothing but E intersection over k running from 0 to infinity ak by n. So it will be a E infinity, as E infinity is a intersection of these two sets, which implies E infinity must be a subset of intersection over k running from 0 to infinity a of k by n. Okay, that is, it is a subset of each ak by n when your k running from 0, 1, 2, 3, and up to so on. So it will be a E infinity whenever k running from 0, 1, 2, 3, and up to so on. But ak by n is a positive set with respect to signed major gamma, in which implies signed major or gamma of E infinity must be greater equal by 0, since ak by n is a positive set with respect to signed major gamma, in which implies signed major or has E infinite a subset of ak by n, but E with respect to signed major gamma minus k by n into mu. So which implies, as it is a positive set, which implies gamma minus k by n into mu of E infinity must be greater equal by 0. Since ak by n is a positive set with respect to signed major gamma minus k by n into mu. So after solving this we get gamma of E infinity is greater equal by k by n major of E infinity. Okay, which is for all k running from 0, 1, 2, 3, and up to so on. So here measure of mu is a measure, and we have given that mu is a finite measure state. Whatever will be the value of measure, gamma of infinity always greater than infinity, but measure is positive. Therefore whatever will be the largest value of measure of infinity, gamma of infinity is always greater than this quantity. It means it must be equal to infinite only, since for any measure it is always greater equal. So there is only one possibility, that gamma of E infinity will be equal to infinity, since for each major value mu of E infinity, gamma of E infinity is always greater equal by this quantity. It means there is only one value for gamma of infinity, which is infinity. Okay, so take this one as some star, and if we take x is belonging to E infinity, but E infinity is subset of intersection of k running from 0 to infinity a k by n. That is, it is subset of each a k by n, which implies x is belonging to a k by n. As x is belonging to a k by n, then it is a positive set with respect to simultaneous gamma minus k by n into mu, which implies f is greater equal by k by n on this a k by n. Again here, whatever will be the value of k by n on a k by n, f of x is always a greater value. Again, there is only one possibility for the non-negative measurable function f, which is its value will be equal to infinity, which implies f of x is nothing but infinite. Take this one as a star, double star. Now here, on the same side will be equal to infinity. So these two concepts, that is f of x will be equal to infinity and gamma of infinity will be equal to, both simultaneously. This, since they are on the same sets a k by n, positive set a k by n, therefore both are same. Implies as f of x is equal to infinity, then integration over say e infinity of f d mu is also equal to infinity. So take this one as a equation double star. Now, as both these concepts are both simultaneously somewhat, then they must be equal. Okay, as they are equal, which implies gamma of E infinity is equal to integration over set E infinity of f d. Okay, so this will be in stable equation 8. Equation 8. And this will be possible when gamma, since then it is possible that measure of E infinity measure will be a non-negative constant. So here first we have considered it will be a greater than 0. That is, it is when measure of E infinity will be greater than 0. But there is one possible value that measure of E infinity maybe will be equal to 0. Now if measure of E infinity equal to 0, if measure of E infinity equal to 0, as measure of E infinity will be equal to 0 and gamma of E infinity is nothing but integration over set E infinity of f d mu, then we get, for measure of E infinity greater than 0, we get gamma of E infinity is nothing but integration over set E infinity of f d mu. If we take measure of E infinity will be equal to 0, and we have gamma is absolutely continuous with respect to mu, as measure of E infinity will be equal to 0 and gamma is absolutely continuous with respect to mu with respect, so implies gamma of E infinity is also equal to 0. But gamma of E infinity is nothing but integration of set E infinity of f d mu, and which is equal to 0, which implies gamma of E is nothing but, gamma of E infinity is nothing but, okay, but this can be written as gamma of E infinity minus of 1 by n measure of E infinity is less equal by integration over set E infinity of f d mu. Since gamma of E infinity is nothing but integration over set E infinity of f d mu. But if we subtract this positive quantity, non-negative quantity, then either it will be equal to this one or less than. Similarly, it is less equal by gamma of E infinity plus 1 by n measure of E infinity. Since gamma of E infinity will be equal to integration over set E infinity of f dv. But when we subtract minus of 1 by a measure of infinity, and this will be always a non-negative quantity, then it is always less equal by this quantity. Similarly, if we add 1 by a measure of infinity, if measure of infinity will be equal to 0, then it is equal to integration over set E infinity of f dv. And if it is greater than 0, that is measure of infinity is greater than 0, then it must be, this quantity must be greater equal by this quantity. So here we get this. So take this one as equation 9. Now adding equation 8 and 9, we get in equation 8 and 9, we get add equation 8 and 9. First equation 8 is nothing but equation 7 and 9. Equation 7 and 9. This nothing but gamma of infinity minus measure of infinity, which is less equal by integration over set E of F of D mu measure of infinity. And equation 7 is nothing but gamma of union over k running from 0 to infinity k minus 1 by n measure of union over k running from 0 to infinity k, which is less equal by union over k running from 0 to infinity k F d mu, and which is less equal by this quantity. After adding this with equation 9, we get implies gamma of union over k running from 0 to infinity ek minus of 1 by n measure of union over k running from 0 to infinity ek. And in that we have to add the equation 9. What is the equation 9? Plus gamma of e infinity minus of 1 by n measure of e infinity, and which is less equal by, as we have just taken the addition, then the infinity as it is, which is nothing but now from here integration over set e infinity of f d mu plus from there union over k running from 0 to infinity of ek of f d mu, and which is less equal by gamma of union over k running from 0 to infinity ek minus 1 by n measure of union k running from 0 to infinity ek, and here we get gamma of e infinity plus 1 by n measure of e infinity. Now if we take its sum, they will be converted in its union. Gamma of union over k running from 0 to infinity ek plus gamma of e infinity, it can be written as gamma of e infinity union over k running from 0 to infinity ek. Okay, since gamma of e infinity union over k running from 0 to infinity ek is nothing but this term plus this one. Similarly, if we take minus of 1 by n common, then this second term can be written as union of e infinity union over k running from 0 to infinity ek, and which is less equal by, these two terms can be written as integration over set e union over k running from 0 to infinity union over k running from 0 to infinity, which is less equal by gamma of e infinity union over k running from 0 to infinity ek plus 1 by n measure of e infinity union over k running from 0 to infinity ek. Okay, but we have defined e is nothing but e infinity union over k running from 0 to infinity ek. First take this one as equation 10. Okay, so we will go to our previous steps. Capital E is nothing but E infinity union over k running from 0 to infinity ek plus 1 by n measure of k running from 0 to infinity ek. Just we have to so infinity union over k running from 0 to infinity ek is nothing but E. So gamma of E minus 1 by n. Again measure of E infinity union over k running from 0 to infinity ek is again E, which is less equal by integration over set E of f d mu, which is less equal by gamma of E plus 1 by n measure of. Okay, so we will get these inequalities. Now subtracting gamma e on both sides, then we get minus of 1 by n measure of E is less equal by integration over set E of f d mu minus gamma of E, which is less equal by 1 by n measure of. Okay, now get integration over set E of f d mu minus gamma of E lies between minus 1 by n measure of E to plus 1 by n measure of E. Therefore, it is actually nothing but That is, this term is bounded by these two terms. Therefore, modulus of integration over set E of f d mu gamma of E. But as mu is a finite major space, we have to treat n as a larger such that 1 by n major of E is less than epsilon. Therefore, from that one we get modulus of integration over set E of f d mu minus gamma of E is less equal by or less than epsilon. Since 1 by n major of E is less than epsilon. That is, we have already chosen such a n such that the 1 by n major of E is less than epsilon. But as epsilon is arbitrary small, epsilon is arbitrary small. So take epsilon equal to 0. As epsilon equal to 0, which implies integration over set E of f d mu minus of gamma of E is equal to 0. As it is equal to 0, then gamma of E is nothing but integration over set E of f d mu, and hence the required result. That is we have to prove. So if capital X curly B mu be a sigma finite major space and gamma is a measure which is completely continuous with respect to mu, then there exists one non-negative measurable function f such that gamma of E will be equal to integration over set E of f d mu, and which is true for now finite major space. After that we will prove its uniqueness, and after that we will prove it is also true for sigma finite major space. Okay. Now first we will prove its uniqueness. Uniqueness. Let G be any other measurable function. Let G be any other measurable function. Other measurable function such that gamma of E is equal to integration of set G d. But already we have proved that, and already we have gamma of E equal to integration of set E of f d. As left hand sides are equal, which implies right hand side must be equal. Therefore, integration of set E of f dv is nothing but integration of set E of g dv. So this can be written as integration over set E of f minus g d, and which is equal to 0. And we have proved one result. If integration over set E of f will be equal to 0, then f equal to 0 almost everywhere with respect to the given measure mu, which implies as integration over set E of f minus g d mu will be equal to 0, which implies f minus g equal to 0 almost everywhere with respect to the measure mu, which implies f is equal to g almost everywhere with respect to the measure mu. Hence, if g is any other measurable function of this property, then it coincides with f, and hence the required result, hence the proof. So here we have proved the result is true for finite major space. Next lecture, I will prove this is also true for a sigma finite major. That is, we will extend it to sigma finite major spaces. Okay. Thank you for watching the lecture.